I'm Christina Holder, and I'm a student at LeTourneau University. My research project is testing the reliability of DNA bind and DNA binder softwares for identifying DNA binding proteins in bacteriophages. So the idea for my project was born earlier this semester while I was doing functional annotation for the bacteriophage dynamo that I had isolated last semester. So as I was looking at functions in a certain operon, I noticed that most of the genes I was looking at were either being identified as DNA binding proteins or hypothetical proteins that I was not able to find a function for. So out of curiosity, I ran the hypothetical proteins in that region through DNA bind and DNA binder. Not surprisingly, many of those proteins had very strong probabilities to be DNA binding proteins in both softwares. However, most of these proteins did not have strong hits in CBI BLAST or HHPRED, meaning I was not able to call a function for them. But this made me wonder if we could trust these softwares in the future to make function calls. So to test this, I chose 6 different clusters with various host and life cycles, and I randomly selected 3 phages from each of those 6 clusters. And then from each phage, I selected 8 DNA binding protein sequences and 7 non-DNA binding protein sequences to run through these softwares. So that totaled out at a total of 270 sequences run. 153 of them were DNA binding sequences and 127 were non-DNA binding sequences. So I represented my data in these charts here as sensitivity, specificity, positive predictive values, and negative predictive values. So that's a lot of terms, and so I'm going to do a quick definition for each of them. So sensitivity is going to be the percentage of DNA binding proteins identified out of the total number of DNA binding proteins run. And then specificity is going to be the percentage of non-DNA binding proteins correctly called out of all the non-DNA binding proteins run. So a higher sensitivity would mean that the software is identifying a higher percentage of DNA binding proteins, which is good. And then a higher specificity means that the software is not calling many false positives, which is also good. So we're looking for a high sensitivity and a high specificity. And then positive predictive value is going to be out of all the DNA binding proteins called, how many were true positives. And then negative predictive value is out of all the non-DNA binding proteins called, how many were true negatives. So the idea for what I was looking for with this data is I wanted to run a combination of both of these softwares if they were to be put into use, like how we do for membrane proteins, where we have multiple different softwares to check. So I wanted to first decide which DNA binder data set would be most reliable. So as you can see here, the realistic data set had the highest specificity, but it also had a very low sensitivity, meaning that it's not going to call many DNA binding proteins, and out of the ones it does call, there are going to be a few false positives sprinkled in there, and we're not going to be able to identify which. So I don't think the realistic would be that helpful. And that leaves main and alternate. So as you can see, main has a higher sensitivity and specificity than alternate. So that means for DNA binder, I think main would be our best bet for reliability. And that leaves DNA bind. So all of these different rows you can see in the DNA bind table are basically the same software, but changing the false positive rate on the website. So the default false positive rate the website gives is 15%, which is relatively high. So I wanted to experiment with some lower false positive rates too. So as you can see, the false positive rates of 1, 5, and 7 gave us a specificity of 100%, meaning that out of the 127 non-DNA binding proteins I run, they do not call a single false positive. So for that reason, I think that one of these false positive rates would be best to pair with the main data set. And although 7% false positive rates didn't call any false positives within this data set, I think that is still a relatively high false positive rate, and it doesn't seem very reliable. So I'm recommending that we either complement the main data set from DNA binder with DNA bind run at a 1 or 5 false positive rate setting. And in future research, I would like to do some wet lab experimentation to get more concrete evidence on the sensitivity and specificity rates of these websites or of these softwares to guarantee that they are actually giving us true calls without many false positives. And I would also like to expand my data set to include more different clusters and more genes to get some more accurate data. But in the end, I think that using DNA binder run at the main data set and DNA bind with a false positive rate or 1 or 5% could be very helpful in identifying functions for some of the hypothetical proteins in bacteriophage annotation.